Tonight we are delighted to have as our speaker Sean Solomon of the Carnegie Institution of Washington. The Messenger mission. After 3 flybys, the Messenger spacecraft is now in orbit around Mercury, and we are now gaining our first global view of Mercury's interior and surface environments and its extremely dynamic relationship with the Sun and with the planetary medium. We will learn tonight about the results so far of the Messenger mission, and we will also learn about a new understanding of Mercury, the solar system's family of rocky planets, and rocky planets in other planetary systems. And as many of you may have noted this past week, the Messenger program was extended for another year, and I hope we will hear about that as well this evening. Dr. Solomon received a BS and PhD in geophysics from MIT. His research interests include marine geophysics and geodynamics, and he has participated in research ranging from oceanographic expeditions as well as expeditions to Venus, Mars, and Mercury. In addition to the Messenger program, he has worked on the Grail mission and on Plume. For the past 10 years, he's also been the principal investigator for Carnegie's research as part of the NASA Astrobiology Institute. And he is a member of the National Academy of Sciences. Dr. Solomon.
Thank you, Robin, for that wonderful introduction. Most gracious. And thank you all for coming to hear about the Messenger mission, the spacecraft now in orbit around the innermost planet. When you think about the word Mercury, that word evokes many things to many people, but among them are heat, speed, and changeability, as well as movies no longer in the theater, coins no longer in circulation, and automobiles no longer manufactured, but that's beside the point. I want to talk about the planet Mercury, which evoked these characteristics. I think Robin called it the Swift planet, thank you. And just to bring everybody into a common context, Mercury is indeed a member of the family of inner planets in our solar system, made out of rock and metal. That includes the Earth. Mercury is, of course, the smallest, closest to the Sun. It is only 5% of an Earth mass, and yet it is made out of material that on average is denser than that of any of the other planets, including our own, from which it has been inferred that Mercury must have a much higher fraction of iron, which is the cosmically most abundant element of the requisite density. And the iron in the Earth is mostly in a metal core, so we think that Mercury has a much larger fraction of its makeup within a central metallic core. We don't know the structure of that core, and you see some depictions here. And how much of the core is liquid and how much is solid. The Earth, of course, has a liquid outer core, which is the source of its magnetic field. Mercury has a magnetic field. It's the only other inner planet to have one, and for reasons that I'll explain. We think that it arises like that of our own magnetic field by convective motions, a dynamo, in the fluid outer core deep in the So Mercury is mostly metal, and with a thin shell of rocky or silicated material, and that imparts its very high density. So one of the interesting questions that the Messenger is going after is how the planets were assembled so that this was one of the outcomes of the experiments that produced all of the inner planets, including our own. And Robin also alluded to the fact that we now know a great deal about planets around other stars. This is a slightly misleading plot to show how Mercury falls within this particular depiction of the extrasolar planets known as there were a couple of weeks ago. And what's plotted is the distance of the extrasolar planet from its host star and the eccentricity, the degree of outer roundness of the orbit of those planets. And Mercury falls in the middle of this cloud of planets is depicted in this kind of diagram. But what is missing is the fact that all of these planets are about the size of Jupiter, and Mercury is much, much smaller by more than 3 orders of magnitude. And we do not know yet of any Earth-like, much less Mercury-like extrasolar planets, but that's on the horizon. So the message from that plot is that we now know that planets close to their host stars are common. Many are inside the orbit of Mercury, but within our own solar system, Mercury is the nearest laboratory for studying the outcome of planet formation near a star like our Sun. Prior to the Messenger mission, only a single spacecraft had visited Mercury, and that was 1975. The Mariner 10 spacecraft was launched from Earth and flew by Venus and then flew by Mercury 3 times. Each of the flybys was 6 months after the previous flyby. And 6 months on Mercury is a solar day. So every time Mariner 10 flew by Mercury, the same side was in daylight. So Mariner 10 was able to image only half the surface, a little less. But it discovered, and it did some wonderful imaging at about a kilometer average resolution per image pixel. Discovered the magnetic field of Mercury, detected the first 3 known species in Mercury's very tenuous atmosphere, a term called an exosphere that I'll describe in a second, and documented some of the very dynamic aspects of the envelope of space dominated by Mercury's magnetic field and full of charged particles from the Sun and from the surface known as the magnetosphere, which is a tiny analog of Earth's magnetosphere, which protects us from charged particles from the Sun. And it's tiny because Mercury's magnetic field, although Earth-like in its geometry, is much smaller than that of our own planet. An exosphere, just because I'm going to talk about this term later in the talk, is the part of any atmosphere where the density of the individual atoms or molecules are so low that there's no collision between individual particles. It is not a gas. It is a group of individual particles that follow trajectories governed by their velocity in the gravitational field. In the top of the Earth's atmosphere is an exosphere. On Mercury, the exosphere is the entire atmosphere, all the way down to the surface. There's just not much atmosphere. There's nothing you can see, nothing you can smell. Ground-based astronomy has done a lot to fill in some of the holes over the time frame between when Mariner 10 flew by Mercury 2 times and the Messenger mission. Prior to Mariner 10, it was ground-based radar that taught us that Mercury is in a very unusual relationship with respect to its spin state versus its period it takes to travel around the Sun, its year. And then the ratio of the spin period to the year is precisely 3:2. And that's a kind of tidal locking, but it's not seen anywhere else in the solar system. And the kind of tidal locking with which we're all much more familiar is a 1:1 ratio, or synchronous rotation, like the Earth's moon, which always presents the same face to us, or many of the moons of the giant planets farther out. But Mercury, the closest planet, of course, to the Sun, is in this unusual 3:2 resonance. And a consequence of that, an odd consequence of the fact that the spin rate is so low, is that the solar day on Mercury, the time between successive passages, say, overhead to an observer on the surface of the Sun, is much, much longer than the spin day, the sidereal day. And the sidereal day is a little less than 2 months. The solar day is a little less than 6 months. In fact, it's precisely 2 Mercury years. So if you were sent to the planet Mercury to explore it, your daylight would last 3 months, and your night would last 3 months. But every night would be New Year's Eve. In addition, Earth-based astronomy led to additional discoveries of species in the atmosphere, sodium, potassium, and calcium, the major constituents of Mercury's atmosphere. And these must be derived from the surface to have the abundances that they do. I'll talk a little bit about that later. Ground-based radar 20 years ago discovered that Mercury's poles have radar-bright material that's high in radar backscatter that depolarizes a polarized radar signal in a manner best matched elsewhere in the solar system by water ice. Water ice on the planet closest to the sun, a planet that at the equator gets to 450 degrees centigrade when Mercury is closest to the sun. And the reason that one can postulate that there is water ice at the poles of Mercury is that the spin axis of Mercury is nearly perpendicular to its orbital plane. And therefore, areas, topographic lows, such as the interiors of large impact basins or impact craters, are in permanent shadow. And because they're in permanent shadow, and because the atmosphere is so tenuous, so that there's no poleward transport of heat as there is in the Earth's atmosphere, these are permanently cold areas. And by cold, I mean less than 100 Kelvin, 80 or 90 Kelvin. Cold enough so that if any molecule of water or other ice-making volatile species ends up in these crater floors, it can stay there, trapped as an ice. And so the postulate is that these radar signals are indicative of deposits of ice trapped in these cold regions on the floors of craters near the two poles of the planet closest to the sun. So that's one of the things we're still working on with testing. And finally, aerospace radar astronomy showed 4 years ago that the motion, the solid motion of the planet Mercury as it traverses its eccentric orbit around the sun, and there's slight but detectable variations in the spin rate over the course of a Mercury year, indicate that the outer part of Mercury is decoupled from the rest of the planet by some fluid layer at depth, which is taken to indicate that the outer core of Mercury must, like that of the Earth, be molten. So that's important when we come to talk about the magnetism. Anyway, the messenger team, including the group at the Johns Hopkins University Applied Physics Laboratory, was in place to design and build and later operate the messenger spacecraft, proposed this mission to NASA 12 years ago, a little more than 12 years ago. And it was selected for flight on the basis of our ability to answer the questions that are shown on this page. We wanted to know why Mercury ended up, unlike Earth and Mars and Venus, with such a high fraction of metal. We wanted to understand the geological history of the entire surface of Mercury and how that related to other planets. We wanted to know why Mercury had a magnetic field when Mars and Venus did not. And what does that have to do with the present state of Mercury's core, which is such a large fraction of the mass of the planet. We wanted to test the idea that the radar reflective materials of the poles are water ice, or if not water ice, what are they? And we wanted to understand the exosphere and other sources of species that are easily mobilized by temperature and other processes, so-called volatile elements and volatile compounds. And we argued that we could answer these questions from an orbiting spacecraft if we flew the right instruments, and that if we did answer them, we would learn important aspects, not only about Mercury, but about all of the family of interplanets that includes our own. However, there's a reason, two big reasons, why it took more than 50 years into the space program before NASA or any other space agency could put a spacecraft into orbit around the innermost planet. And here are the two biggest challenges. One is slowing the spacecraft down, and the other is surviving once you get there. Slowing the spacecraft down is a challenge because Earth and Mercury travel around the sun at different speeds. And a spacecraft you send from Earth starts out with Earth's velocity around the sun. Mercury is a small object, and so to be captured in its gravity field, you've got to take along a propulsion system that can slow you down so that you are captured. And without extraordinary efforts, the speed that a spacecraft would be traveling relative to Mercury, but when it accomplished a transfer from the Earth to Mercury, would be about 10 kilometers a second, and that's too large by about a factor of 10 compared to the propulsion system we could carry in our spacecraft. So we had to solve that problem. We knew how to do that. And the other is that, of course, Mercury is the planet closest to the sun. The sun is extraordinarily hot, and you must protect the spacecraft from both the sun and from the side of the planet that is exposed to the sun itself and re-radiating energy back as heat. So that was a mix of engineering design challenges. The Messenger spacecraft addressed those challenges in a variety of ways. It built a large sunshade to protect itself from the sun and covered the front side of that sunshade with a ceramic cloth that was commercially available and used to wrap shuttle main engines. The result of using that sunshade was, and we tested this on the Earth long before this spacecraft was put together, was that the temperature on the sun-facing side of the shade could get as high as 350 degrees centigrade at Mercury's closest distance from the sun. And even so, the backside of the sunshade, which had some other layers of insulation behind it, could operate at room temperature, which meant that we didn't have to go to any extraordinary lengths with respect to high temperature electronics. Radiation hardened, but still standard semiconductor-based electronics. Now, solar power is abundant when you're that close to the sun, but the challenge is to have solar rays that operate at high temperatures. And that was accomplished by choice of materials for the solar rays, by having some big solar rays that are as much mirrors as two-thirds mirrors, and twice as much mirrors as there are solar cells, and by having the solar rays be able to be articulated, to have the attack angle change with respect to the distance, to the direction to the sun, so that you could control the temperatures at which they operate. And finally, we needed to have a spacecraft that was primarily a large rocket engine, because we knew we had to impart a large change in velocity to get captured in the orbit. So this spacecraft was a bunch of fuel tanks and a structure built around those fuel tanks and a propulsion system and some instruments bolted to that spacecraft launch. When Messenger launched, it was 55% propellant, so that we needed to be able to make those maneuvers. The other way we addressed the challenge of slowing down enough so that our propulsion system could have achieved orbit insertion was to make use of planetary flybys as a way to substantially change the speed of the spacecraft through the successive encounters. The theory for how to do this had been worked out 25 years earlier, but we were making use of those theories so as to be able to do an orbit insertion with a small spacecraft and a modest propulsion system. But it meant that we had a long journey, depicted in this timeline at the bottom, and shown here from the north celestial pole of the solar system as more than 15 revolutions around the sun. So we launched from the Earth, we flew by the Earth a year later. We had 2 flybys of Venus in 2006 and 2007. The launch was more than 7 years ago. And that was followed, as Robin had mentioned, by 3 flybys of Mercury, which were very important, not only for making it possible to do the orbit insertion, but for giving us our first glimpse in more than 30 years at close range of Mercury, and an ability to train all of our instruments onto a planet and learn how they operated in Mercury's environment. And they were interspersed with large propulsive maneuvers, where each maneuver targeted the spacecraft trajectory for the next flyby. And then finally, after the 3rd flyby in September of 2009, we had to wait 18 months until last St. Patrick's Day when we could do orbit insertion. The instruments that we carried were the ones chosen to answer the questions that framed the entire mission. And they're shown here, and I'll show you results from many of these in a few minutes. There's, of course, a camera, an imaging system. It is the only instrument that has a degree of freedom in its pointing that is independent of the spacecraft, because it's a scan platform. All the other instruments are fixed to the spacecraft, and so pointing consists of moving the spacecraft. Here's the sunshade again. There are several chemical remote sensing instruments using gamma rays, using X-rays, using neutrons. There's a magnetometer at the end of a long boom. That's done to get away from magnetic fields generated by the spacecraft itself. There's an altimeter using a laser to range to the surface of the planet. There's a very high spectral resolution spectrometer that goes from the ultraviolet to the near infrared, that looks at the atmosphere and looks at the surface. I'll show you some results from that. And there are two charged particle detectors that determine the energy and the mass per charge or composition of particles in the vicinity of the spacecraft, ranging from low energy plasmas up to high energy particles. So it was a good blend of instruments that addresses many planetary phenomena and appropriate for the first spacecraft to orbit any planet, but in particular Mercury. My wife, who's in this audience, and I enjoyed the opportunity to see Messenger launched a little over 8 years ago. We had 3 of our grandchildren with us, and it was a marvelous night. We managed to fit the launch in August of 2004 in between a tropical storm and a hurricane. Always fun to try to do a launch in August, but we got off on the second day of our launch window. I'll be showing only a few results from the flybys because they've been digested and you want to hear about the new results from orbit. But I do want to mention that a little bit about the geometry of the flybys. These, of course, gave us the first data of Mercury since Mariner 10 in close range. They all involved flying nearly in the equatorial plane of the planet. We're looking down in all cases from the North Pole. Approaching on the night side, the anti-sunward side, closest approach of about 200 kilometers on the night side. And observations of the day side of the planet, mostly on departure, looking back as we flew away. These were in early 2008, fall of 2008, fall of 2009, until we finally went into orbit. And that happened this year in March, St. Patrick's Day evening. We flew for the first time over the North Polar region with a big gap in our imaging coverage, fired our propulsion system for 15 minutes, and went into a near-polar orbit. And we've been in that orbit since March. You see some of the characteristics of that orbit in cross-section. Imagine the sun is off to the left, and the charged particles and interplanetary magnetic field that are streaming away from the sun's upper atmosphere, the solar wind, are coming in from the left. And here you see some of the characteristics of Mercury's magnetospheric envelope, a miniature Earth's magnetosphere. The Messenger orbit is a 12-hour orbit. It's a pretty eccentric orbit in which our closest approach is 200 kilometers and at about 60 degrees to 70 degrees north. A nearly polar orbit inclined 82.5 degrees to the equator of Mercury. We went into this 12-hour orbit for a variety of reasons, but the principal one was for thermal design. Every time we approach the day side of Mercury at close range, the spacecraft is markedly heated by radiation from the sunlit side of the planet. And we have to absorb that heat. We can't, this is the object we're trying to study. We can't put a shade in front of, between the planet and our spacecraft. And we could not survive a low altitude circular orbit. But we used this high altitude part of this very eccentric orbit to radiate the heat we absorb from the planet back into space. That and the choice of other orbital characteristics all came out of the thermal design. Okay, let me say a few words about the magnetic field, and I'll go through a few other topics and illustrate what we're learning, especially from the recent orbital observation. This is just where we were before we went into orbit. We had flown by, at this point, 2 times. Mariner 10 had flown close enough to the planet to sense the magnetic field 2 times. Our second flyby was the first time that any magnetic field measurements had been made on the western hemisphere of Mercury. And this is a typical flyby where you see that as you get close to the planet, the magnetic field magnitude is going way up, and it's confirming that Mercury is indeed its source of an internal magnetic field, and that it's like that of the Earth. It is dominated by a magnetic dipole, meaning the form of the magnetic field is that of a bar magnet, a giant bar magnet we have near the center of the planet. What we've learned from orbit is that unlike Earth, the best location of that dipole in the center of the planet is not the center of the planet, but is substantially offset. This represents the first several hundred orbits of the planet, and what was measured to determine a little bit more about the geometry of the planet was the location of the magnetic equator. On average, over the last several thousands of years, the Earth's magnetic equator would be pretty closely aligned with the geographic equator. It's not aligned instantaneously, so you have to do that energy. On Mercury, the magnetic equator, where the magnetic field is parallel to the spin axis, is systematically located north of the geographic equator by about 500 kilometers, which doesn't sound like much until you realize that Mercury itself is a small planet. It's only 2,400 kilometers in radius. So this offset of this magnetic field center is 20% of the radius of the planet. It means that the high latitude field is stronger in the north than in the south by a big factor, more than 3. It means that area of the surface with magnetic field lines are open to the solar wind outside of Mercury's magnetosphere, and therefore are available as avenues for charged particles to come roaring down and hit the surface and modify the surface. Is much larger in the south than in the north. And it presents a geometry for a magnetic field that's strongly aligned with the spin axis, but strongly asymmetric about the equator that we've not seen before in the planet. So Mercury's magnetic field is novel, and it's now challenging the theoreticians to come up with explanations for what we see. Now a few words about this wonderful but very tenuous atmosphere that Mercury has. On the left, you see a cartoon of some of the sources of the species in the atmosphere. Mercury's atmosphere, unlike that of the Earth or Venus or even Mars, is not permanent. It is constantly lost to space. And it therefore must be constantly renewed, and the renewal processes are depicted here. Heat or ion impact or dust impact kicks material off the surface and imparts an energy to the individual atoms or molecular species. And sets them off on ballistic trajectories. Remember, there's no interaction, no collisions between particles. And there's an interesting phenomenon that was first predicted and then observed by Earth-based astronomers, that if you loft atoms high enough off the surface of Mercury, some of them, depending on the species, can be very sensitive to sunlight. And sunlight can push them away from the planet. The force of the photons hitting the atoms is enough to push them away. And as a result, Mercury has a comet-like tail. A tail of atmospheric atoms that have been pushed away from these high trajectories and extends in the direction opposite the sun for huge distances, as much as 2 million kilometers, as has been documented for sodium. Anyway, Messenger flew through that tail and was able to make some of the earliest high-resolution observations of the structure of the tail, and to look for species other than sodium in that tail. Remember that the spectrometer that we're using is attached to the spacecraft, which then had to nod around the Sun-Mercury line as we were flying toward the planet to make these measurements. This is looking at sodium. It's a particular wavelength at which sodium emits in response to excitation by sunlight. And that emission line can be measured very precisely by a spectrometer. And the total column intensity of that emission is colored here. And then the higher colors being the higher values, and then you contour this, and that gives you an integrated view of what you're seeing for the sodium tail near the planet. Remember, this goes out for 2 million kilometers. I'm sorry, this is in miles. It's for a press conference. You see, it's also an interesting spatial distribution with a stronger emission at high latitudes than at low latitudes in some asymmetry. During subsequent flybys, we went through the tail 3 times and discovered that magnesium is a constituent of Mercury's atmosphere. Magnesium also has an emission line, but you can't see it from the Earth. It's in the ultraviolet. Calcium, which was detected from Earth, is seen as well in this tail, and the distribution of species are different in the tail. With sodium enhanced at high latitudes, calcium enhanced at low latitudes, and magnesium evenly distributed. And the messages that we got out of this is that there's a complicated mix of processes, and the signature of that is the different atoms have different distributions. So they're responding to this different mix of processes in different ways, and the fact that we can look at multiple species gives us promise that we can sort out what's going on. We also saw strong variations between flybys in strength of detail. You can't see it when plotted on this scale, but there's very weak emissions seen during the third flyby compared to the second, down by a factor of 20. And that's simply because Mercury was at a different position with respect to the sun and was moving at a different relative velocity to the sun. And so both of those phenomena affect what we can see, and this was an expected seasonal variation. The charged particles spectrometers on Messenger also allow us to make an inventory. This is from the flyby, that's a nice cartoon, of the ions that are that fill the magnetospheric body. Yeah, you're seeing as we imagine this flyby going through the signature of ionized hydrogen protons from the solar wind and a typical heavy ion, sodium, as a function of position in the trajectory. We just went through closest approach here, and we're now departing from the planet on this particular flyby. And what you see is that the entire magnetosphere is full of ionized atoms from the sun or from the surface, and most likely either ultraviolet ionization of neutral species in the atmosphere or directly ionized species by some surface process. Much of what we have learned about Mercury has come from imaging, and I want to talk about several of the geological processes that we've learned a great deal about from imaging, first from the flybys and then from some orbital observations. Here you see simply a coverage map. When we only had Mariner 10, the region outlined in green was the 45% of the planet seen. And we were lucky that the flybys by Messenger were not spaced evenly by solar day, so that the first flyby and the second flyby saw substantially different areas in sunlight, and we were able to fill in much of the unknown part of the map of Mercury's surface even before we went into orbit. And even the third flyby added some material. So we had about 98% coverage at some resolution and some lighting, even before orbitization. But lighting matters a great deal, as does resolution. And this is a wonderful example of an area that was imaged by Mariner 10 and again by Messenger. And the resolution is not too different between these particular images. They both came from flybys. But the illumination by the sun is what differs these regions in these two images. So here you're seeing only grazing incidence by the sun. So the sun is off to the right, and areas that show up as topographically rugged catch the grazing sunlight and bring out a lot of structure in this double ring basin and some of these impact features and some of these fault structures. Whereas this Mariner 10 image of the same region has sunlight almost directly overhead. And I defy you to even see some of these features clearly under this kind of imaging. Now, both kinds of imaging has its purpose. This kind is very good for distinguishing variations in color. But for seeing landforms, there's no better way than to have grazing sunlight so that you see shadows and can pick up landforms. So both kinds of imaging are important. Now, we make a lot of use of color, and I want to say a few words about that. Mercury doesn't show much distinctive variations in color, but they're there. It's dominantly gray or brown-gray to the human eye, so-called true color. But there are variations, and these variations in color and brightness can be accentuated using image processing methods, such as these, which are the parts of Mercury that were seen by the spacecraft after the first and second flyby, opposite sides of the planet, and showing you that there are variations in relative brightness and in relative color, with some areas redder and some areas bluer, and not too much of a difference between the hemispheres and the types of terrains that are depicted. It's still a leap to go from color and brightness to learning more about composition, and we're starting to do that because we have chemical remote sensing instruments. But we needed the long integration times that orbit provides to do the chemical remote sensing. I will talk about that. But here you see an important area that was provided some further lessons on the important geological process of Mercury that had been a matter of debate for more than 30 years. And that question was whether, as on the Earth and on Venus and on Mars, and to a lesser extent on the Moon, volcanism, the eruption of molten lavas from erupted from areas of depth where rock had been partly melted, was an important geological process for modifying the surface terrain on Mercury and for giving clues to what material lies beneath. One of the areas that had been seen by Mariner 10, but not in great color and not completely, was a huge impact structure, 1,500 kilometers across in Florida. And what the first flybys taught us was that there are planes, smooth planes, inside Florida that are red and bright, and planes outside that are darker and more blue. We learned that these planes are younger than other terrain in this area, and that was one hint that volcanic processes are going on. But around the edge of Florida were also areas that looked to have all of the characteristics that we associate with volcanic centers on other planetary bodies. Here's one of these in great detail from the very first flyby. So this is the Chloris Basin here. This is this feature at the edge, 100 kilometers across. And what are those distinguishing features? There's an irregular vent, an irregular depression that lacks raised rims. Beyond which is an apron of material that is brighter and differing in color from its surroundings, and that apron is draped over terrain, older terrain, such as ejecta from this impact crater. That there are smaller candidates, there are smaller versions of this irregular vent elsewhere on these deposits. And this kind of collection of geological features is seen elsewhere on other planetary bodies, and this is an example of the Moon. A more oblique view of a volcanic center that has been samples from which have been returned to Earth in the Apollo collection, so that we know that there's a volcanic origin for this vent, and the material around it, which is also distinctive in color and brightness from its surroundings, has a volcanic origin. Moreover, it has an explosive volcanic origin, the kind of volcanic eruption that demands that during the ascent of the molten rock, there was release from the rising magma of gases that expanded faster than the magma could move, driving the kind of explosive eruptions that we associate with volcanoes around the rim of fire on the Earth. Now, in orbit, we can get much higher resolution images. This particular vent, some 20 kilometers across, is shown to be quite complex, and among the features that are being confirmed by the high resolution images are the fact that the apron has subdued the topography surrounding it as if it were deposited from above. That there are multiple superposed depressions within this central area thought to be the source of the surrounding deposits, and there are important variations in brightness, particularly within this area. But all of these are consistent with an origin of this feature as a volcanic vent. There are dozens of other examples around the planet of similar vents marked by irregular depressions, surrounded by aprons of bright material that differ in color from their environment. And these are all candidates for past volcanic centers that were sources of these explosive volcanic eruptions, and they're crisscrossed along the planet. We also saw some very interesting evidence for comparatively young volcanism. Everything's comparative. I mean, the planets are 4.5 billion years old, and the very largest impact structure on the Moon, and by inference the other inner planets, are nearly 4 billion years old. And many of the large expanses of volcanic plains on Mercury and the Moon are nearly as old as these young impact structures, meaning that they're in excess of 3 billion years in age. And so the question has always been, for an object like Mercury, what was the duration of geological activity, including volcanic eruptions? And so this feature was very important from the third flyby, It is an impact crater, technically a basin, a Pickering basin, about 250 kilometers across. The inner ring is inside the inner ring is a lighter plains unit that you can see reaches this ring and appears to have flowed out into the surrounding angular material. For a variety of reasons, it is thought that this is evidence for volcanism, that it placed these plains after this crater formed. This material is different in color, it's lower, it is much less sparsely cratered than the surrounding terrains. It's associated with this candidate pyroclastic bed, and as I mentioned, it seems to have flowed out over the ring. This basin is very well preserved, and is one of the youngest intact structures on Mercury, and yet these volcanic deposits post-date this young basin, and therefore we're looking at volcanic material that must be much younger than most of the volcanic plains on Mercury, and indicate that volcanism extended over most of the history of the planet. From orbit, we're getting very high resolution views of volcanic phenomena. And here you see an example of a region that has been substantially modified by volcanic flows that probably erupted from these vents here, created channels by thermal and mechanical erosion in the surrounding terrain, carving little islands in the middle of these channels, breaking the rims of these channels that flow out over surrounding countryside, and filling in low areas like this large impact structure to depths of several kilometers. So we've gone from a position where the question of the importance of volcanism was debated following Mariner 10 to having sufficient details of individual sets of volcanic eruptions to be able to do physical volcanology, to be able to understand the eruption rates and some of the lava characteristics of volcanic terrains on the planet. And that just says that for people who just repeat what I said. It was known from Mariner 10 that Mercury has also experienced substantial faulting, and that the kinds of faults that are most spectacular, most abundantly seen by Mariner 10, were called lobate scarps. They're topographic cliffs or scarps that have a lobate curved platform. And they offset the topography by 1 or 2 kilometers. And sometimes you can see examples of pre-existing features like this impact crater that have been cut in half by this fault system. And these characteristics in combination indicate that this cliff is the top of a great fault that involves horizontal shortening of the surface. So that the material on the right side of this image has ridden up and over the material on the left on a great fault system at depth. And the fact that these kinds of fault features were seen everywhere on Mariner 10 led more than 30 years ago to the suggestion that they are a product of cooling and contraction of the planet. And the prediction was that wherever we looked with messenger images, in places that Mariner 10 had not viewed, we would see many more of these lobate scarps. And that is indeed what we have. This one seen for the first time by messenger and named after the ship Pico. So this is probably the only planet in which its history of cooling and contraction has a readable geological record in the history of faulting at the surface. But we're learning from orbit that the tectonic history, the history of deformation, is much more complex than that. At high modes and latitudes, we learned from the orbital observations, there are huge volcanic plains that fill pre-existing craters and basins to depths of several kilometers. And many of these nearly filled craters, you can barely see that there was a crater underneath it, but there's a circular ring of high topography that marks the rim of the earlier crater before it was buried by volcanic infill, has been substantially deformed by these intricate patterns of frost. They're almost certainly, at least partly, related to cooling of these great thicknesses of lava. And the floor of the great impact basin Dolores has a much more complicated history than we appreciated with features involving stretching and producing these troughs, and features involving shortening and producing these ridges, all intertwined over successive periods of deformation of the region like this. And this is an example of some of the high-resolution views that we're getting now from orbit, including this remarkable area in the center of Chloris, where there's a radiating pattern of troughs called Fosse, which was originally called the Spider in press releases about 3.5 years ago. With more than 200 of these troughs radiating from a region in the center of the basin. We're still debating what the origin of these features are, but they involve large-scale stretching in a very symmetric way around the center of the basin of the surface to produce these tectonic features. The color imaging has shown us a great deal about variations in composition on the surface, and these high-resolution color images that were obtained from our second flyby were put into a wonderful imaginary flyby in which you are viewing the surface in exaggerated color as you're flying over it. And you see great fault systems that have disrupted craters. But I draw your attention to the colors and their variations because this flyby shows you that impacts can bring up to the surface material different in color from the surrounding terrain. So this rim and these central peaks are telling us that there's different material at depth than there is at the surface. This crater threw out materials different in color on one side, but not on the other. This area was penetrated by craters that brought up more red material by virtue of the impact excavation itself. More blue material was excavated by this impact region, more red material here. So we're getting a three-dimensional view of variations in composition, where the epoxy composition is the color we see in the image, leading to the notion that Magnetism put out a couple of years ago, that not only was volcanism important on the surface of Mercury, but almost everywhere we look, we're seeing variations in composition that we can associate with variations in composition elsewhere on the planet among volcanic flow units, except some of these variations are only seen because craters have penetrated to a unit that is different in color and composition and depth and brought some of that material to the surface. And so that the outer several kilometers of Mercury must be a product of successive emplacement of volcanic units differing in composition from one another, but spanning a range of compositions that is similar to what we see on the surface today. So it was completely turned around our view to one in which volcanism dominated the whole formation of the outer crust of Mercury. Just want to show you a few results from topography and gravity. This is from the laser range finder showing that the topographic variation on Mercury is about 10 kilometers. The North Polar region is a region of lowlands. You can see highlands, particularly near the equator. The gravity field doesn't have that resolution of the topography, but there's some similarities between gravity and topography. The combination of the two is giving us the ability to make maps of crustal thickness on Mercury, showing us that the crust is thinner at high latitudes. The altimetry is really only in the northern hemisphere because of our eccentric orbit. The thickest crust around the equator, some important long wavelength variations in topography and crustal thickness that we're still trying to understand, but a total range of crustal thickness of tens of kilometers. So this is another route by which we are working on three-dimensional structure, including of Mercury's outer layers. Remember the high radar backscatter in the polar craters. This is a map obtained at radar wavelengths from backscatter around the North Polar region, and you see these areas thought to be perhaps waterized in the floors of high latitude craters. We don't have the results yet on what the composition of that material is, but we are testing the idea that these are impermanent shadows, and we're doing that in two different ways. We're doing it first with altimetry. Here's one of these craters that is known on the basis of Earth-based radar to host radar bright deposits. And we've flown over this crater enough times to make a complete topographic map of the crater. With this topographic map and its location and the broad topography around it, we can calculate the places where sunlight intersects the surface at different times of Mercury's year, and therefore determine those areas that do not see sunlight at all during the year and must be in permanent shadow. And in the case of this crater, there's good correspondence between that calculation and where the radar bright deposits are seen. You see here successive images of the south polar region, and we're doing a similar experiment only with the images. And we're looking carefully at the regions near the poles to learn which ones never see sunlight in the course of a complete Mercury year. Here again, the areas that are seen in permanent shadow on the basis of imaging are correspond very well to the areas that Earth-based radar says have radar bright deposits. So we haven't yet confirmed that those radar bright deposits are water ice. The jury is still out, but we have a good instrument that will provide that information with enough time. But we have made an important test of the idea that these are permanent cold traps for ice and other materials by testing the topography and by directly imaging the shadows. In the next to last topic, I want to talk about the composition of Mercury's surface. This was absolutely a key goal of the Messenger mission because we thought that by measuring the composition of the surface, we could test ideas for how Mercury ended up a planet that was mostly metal with this huge mass fraction made up of the iron core. There's two instruments on Messenger that are particularly well suited for chemical remote sensing at the level of individual elements. One of them is this X-ray spectrometer. This cartoon illustrates how it works. The sun is the source of X-rays. Both the quiet sun and especially the solar flares give off X-rays. Those X-rays impact the surface of Mercury. They are incident on the surface of Mercury. And they can excite atoms on the surface to fluoresce at X-ray wavelengths. And there's a particular set of lines for each of the elements that are susceptible to X-ray fluorescence that are diagnostic of what's there. So you can do modeling if you know the X-ray flux coming out of the sun, and we have a solar X-ray detector, and you know the characteristics of our planet sensing X-ray spectrometer. You can model the observations here in black with a model for the composition of the surface put through in effect, a simulation of our instrument, and that's shown in red. And that allows you to see many of the major rock-forming elements: magnesium, aluminum, come back to sulfur, calcium, titanium, iron. You don't see iron in solar flares or this very energetic X-ray. But the composition that we are determining for Mercury over large areas and small are not what we're expecting. Here you see two ways of comparing element ratios: magnesium to aluminum, calcium to aluminum, both normalized by silicon, of Mercury areas through X-ray fluorescence, shown in these pink purple dots, against lunar lunar rocks, islands, and volcanic marks, and typical terrestrial ocean floor rocks and continental rocks. And what you see is that Mercury is not like the Moon in composition in these elements. It's not like the seafloor. It's not like the average continental crust. And there are rock types that are different in composition on the Earth. These are mantle-type rocks, very rich in magnesium. There's also a kind of volcanic rock on the Earth called the Carnegie that is confined to the oldest part of Earth history, but it's very magnesium-rich and is thought to be a product of melting at very high temperatures and high degrees of melting to produce a very unusual, very fluid rock. And the Mercury rocks look intermediate between typical volcanic rocks and basalt and these commodities. So Mercury clearly has its own distinctive signature in these major elements. But some important minor elements are big surprises. Titanium was expected by some theories, but it's very minor on the surface. Iron is low on the surface. Remember, there's a lot of iron in the metal in the core. but the iron abundance on the surface is small. This is iron in any species. This is inferred indirectly from spectral reflectance measurements, but that didn't include all the forms of iron, which is studied. But the big surprise was sulfur. Sulfur is seen as a shoulder on this broad line attributed to magnesium and silicon, and forward modeling can distinguish substantially different ratios of sulfur and silicon. And the sulfur abundance, 1 to 4 weight percent, is high relative to other planets. It's 10 times the average for the Earth. And why was this a surprise? It was a surprise because sulfur is an element that is regarded as volatile, as easily boiled off the planet by processes that involve high temperatures. This is the planet closest to the sun. It was thought to be born of high temperature processes, either high temperatures around the young sun and the disk of material out of which the planets were assembled, or by some high temperature process that gave rise to Mercury's high metal attraction. And yet here is a species that should be expelled from the planet during any high temperature event that is more abundant on the surface than that on the Earth by 5 factors of 10. Big surprise. This just shows the footprints of a dozen and a half solar flares, many of which are fairly broad because the spacecraft was high off the planet, some of which are small enough that we can begin, particularly with data since this map is prepared, mapping the variations and comparing those with geological maps. Just an aside on the sulfur, there's some very strong correlation of sulfur with calcium, a much weaker correlation with magnesium, suggesting that perhaps the sulfur on the surface resides in minerals that are sulfides, particularly calcium and sulfur, which is important, an interesting question of how the sulfur got. The second instrument we use for chemical remote sensing is gamma ray spectrometry. That combines gamma rays from natural radioactivity, which I'll talk about here, with more complicated sources of gamma rays involving interaction of cosmic rays with the surface that generate neutrons that, when captured, result in the release of gamma rays that are diagnostic of other elements. But I'll just talk today about the natural radioactive elements. And you see an example of how this is done for potassium. There are two complicated gamma ray spectra where counts per time are plotted versus energy. And the red plot is what is seen at very high altitude off the planet. And you see there's a lot of peaks, and that's telling us that there are gamma rays coming from the interactions of natural decay of charged particles with the spacecraft, energetic particles, cosmic rays. But here's the plot taken at low altitudes, less than about 400 kilometers. And you see the same peaks generally, except for this one for potassium and these two for silicon, indicating that the difference between these two plots is a signature of what's coming from the planet. And so potassium line and similar lines from uranium and thorium allow an assay of the abundances of these radioactive elements on the surface of the planet. And here you see an interplanetary comparison with lunar data in blue, Mars data in gray and black, some typical terrestrial values in green, and the Mercury values in red. The potassium is also thought to be a moderately volatile element that is lost during high temperature processes. We think the moon was born by a high temperature process involving the collision of a Mars-sized object with the early Earth, throwing off enough debris around the Earth so that the moon could accrete from that material. But that process is sufficiently energetic that it depleted the moon in elements that are volatile, such as potassium. Well, Mercury's potassium-thorium ratio, thorium is not volatile, looks like that on Mars, although it doesn't look like that of the moon. And so the kinds of processes that left their imprint on the volatile species, such as potassium on the moon, are not seen. Mercury looks to have similar abundances, or at least ratios, to the other major planets. And the final topic is also related to volatiles, and that is the discovery from the orbital observations of a whole new class of landforms that we didn't see from the flybys, that wasn't known from the region, and have been given the name hollows. They're all associated with impact craters, such as this impact crater up here. They're in particular associated with bright deposits that are on the floors or walls or central peaks of impact craters. But the hollows are depressions, they're holes. Irregular in shape, with no raised rim, sometimes flat floors, often bright, either on the floors or in the halo surrounding them, or both. They range from tens of meters to kilometers across. They sometimes occur in families of hundreds or thousands. And they only occur on this bright material that has been brought to the surface by the impact crater, the impact explosion that created this crater. And so the question is, what are these hollows? They're geologically young because they don't have craters on top of them. But the best idea that has come out of the team is that what we're seeing is the removal of material that is easily susceptible to removal because of heating from above by the sun, or heating from below by magma, or impact of ions and small dust particles that removes material that is weak and easily lost to the atmosphere and eventually to space, creating these holes and these collections of etched terrain. So this is a signature, we think, of some volatile constituent that is present in these bright materials, that is stable at depth in Mercury, but is not stable at the surface, that is brought to the surface by these impacts, and then is progressively lost to the atmosphere and to space by some combination of these processes. So how did this material get there? Well, maybe it was deposited from the gas phase, say at nighttime after a volcanic eruption. Maybe it was actually placed at depth and only exposed later by impact. The jury's still out on that, but it is another indication that Mercury is surprising us, the planet closest to the sun, having active geological processes driven by the removal of some volatile constituent, possibly related to the sulfur or the potassium that we are seeing, but we haven't identified it. That was not expected on the planet closest to the sun. So that's where we stand today. We went into orbit with a 12-month primary mission. That's only 2 solar days. It allows us to see each part of the surface only twice in this given type of sunlight. And we're now on the second of those 2 solar days. But as Robert mentioned, we were just approved for an extension, a second 12-month extended mission, so we will have a second year of observations. And we've designed a quite different set of observations to take advantage of that second year. And I'll close with this preview of what's to come during the extended mission. We're going to have a slightly different orbit and a slightly different cadence of lowering the closest approach altitude, so that we spend more time closer to the planet than we have in the primary mission. More opportunity to collect very high resolution chemical, imaging, topographic, and other information. We have a broader range of scientific objectives because a lot of the objectives of the primary mission involve mapping and collection of global data sets that we've now accomplished. So we can now address a variety of very specific targeted questions and observation campaigns matched to those objectives. And finally, what's shown on here is a depiction of the so-called solar cycle, or the sunspot cycle, which governs the rate of activity on the sun. Solar storms, sunspots, and energetic events that involve streams of particles and radiation from visible to X-rays coming from the sun. And in that, some useful context is the observations made to date are depicted by these arrows. Relative to the most recent solar cycle, the phase of the solar cycle seen by Mariner 10 was one of a waning solar activity. So it was actually 1974 and 75, but that's equivalent to 2005. 2006, 2007, of waning solar activity. The messenger flybys in 2008 and 2009 were a period of extraordinarily quiet sun. Sun was more quiet than it had been for the last century. And only now is the solar activity picking up, and we're seeing that at Mercury through coronal mass ejections, through solar storms, through enhanced radiation, and it's changing the dynamics on a very short time scale of the magnetosphere and Mercury's exosphere. And the extended mission will get us closer, although not quite all the way, to solar maximum. So we expect that the solar activity will continue to increase, and we'll see new phenomena and new manifestations of the extraordinary range of dynamics that goes on between our star and its nearest planet. Anyway, we're looking forward to another nearly a year and a half of observations, and I hope we'll have more surprises to share with you when we're all done. Thank you.
We do have time for questions, and since it's hard to hear in this room when you're asking your question, if you would please stand and speak up.
Require the first person to stand in the front row.
Yes. I was impressed by the double ringed
Yes?
craters,
Yes?
and I don't imagine there's a double ring ceremony between the gods or anything. Can you explain how we get a double ring? I'm ignorant on that.
Yes, in a limited way. All impact craters are products of the explosion that occurs when a meteoroid, or if larger, an asteroid, comes in at high velocity and impacts the surface. When those impacting objects are comparatively small, you get a simple crater with a bowl-shaped floor and a rim, a raised rim around it, and then ejecta formed of material thrown out from that crater that created at the time of the explosion. And for larger and larger objects, the form of the craters, we know from very careful studies of the moon, we know from studies of craters on the Earth, we know from scaling arguments from craters created artificially by large explosions on the Earth, that the morphology, the shape and geometry of the impact crater that's produced by that explosion changes as a function of size. You go from the simple bowl-shaped craters to more complex craters that have terraced walls and more complicated floors. And still larger craters also have a central peak that is thought to be the result of rarefaction, bringing material from particularly great depth on the crater during the collapse of the depression that forms at the time of the actual impact. This collapse is nearly instantaneous, but then it happens on time scale, seconds to minutes after the impact occurs. And then when you go to still larger crater forms produced by the impact of still larger object, that central peak actually becomes a ring. And it's thought still to be the result of the collapse of what's called the transient cavity, the transient crater formed by the initial explosion. But it can be modeled, it can be simulated in impact experiments. We see analogs on all the other interplanet craters are probably the best idea to believe. And still larger impacts produce more complicated 3- and 4-ring structures. The details are, I can't pretend are completely understood, but the kinds of computer code that have been developed to understand the consequences of nuclear explosion have been applied to the impact crater in top of it. And they're very sophisticated codes, but they're still sensitive to assumptions about equations of state, material properties, approximations you have to make to very complicated dynamics where everything is nonlinear and you've got shocks. But a lot of the characteristics of craters have been reproduced by these calculations. So the answer is that the central ring was formed virtually at the same time as the other by the response of the medium to the large explosion. Yes, sir.
Just questions. Where do the neutrons come in with that neutron detector, and not where do they come from? And two, a few years ago, I read some theory that Mercury had a solid iron core and that magnetism was mostly ferromagnetic. Is that theory out?
Part of it is certainly out. Most of it may be out. But let me answer your first question first, and then your second. The neutrons are produced by cosmic rays. So the cosmic ray interaction with the near-surface material produces neutrons, some of which produce the gamma rays that we detect with the gamma ray detector. But there's a spectrum of neutrons that are enhanced near the planet, and they're all the product of the cosmic ray bombardment of the surface. And the neutron spectrometer is looking at how the surface affects the energy spectrum of the neutron. And we have a neutron spectrometer because hydrogen on the surface is a pretty strong modifier of the energy spectrum of neutrons within an energy range that we can sense. And on Mars and on the Moon, hydrogen is enhanced at high latitudes. It is now known because of ice. And you can see that very clearly in the neutron spectrometer.
Is there sulfur up there?
Well, there's sulfur everywhere we have looked, and we would expect to see sulfur. Well, it depends on the form of the sulfur. If there were elemental sulfur, it would be stable as a solid at high latitudes, not only within the floors of impact craters, but at all the high latitudes. But we suspect the sulfur, on the basis of the chemical measurements we've got so far, are probably the sulfide rather than elemental sulfur.
And that's solid core.
Second question. Prior to our flybys, as you have stated, an alternative theory for the observed global magnetic field of Mercury was that, like the Earth, it once had a convective dynamo in the core, but that convective dynamo died. But when it was operating, it magnetized the crust, and that there was some mineral in the crust that required a permanent magnetization. And that what we're seeing today is the field external to that magnetized shell. First, we now know, on the basis of the independent radar observations I mentioned earlier, that Mercury does have a fluid outer core. It decouples the solid body motions of the outer shell from that at greater depth on the time scale of the Mercury year. So we can no longer assume or even postulate that Mercury's core is solid throughout. There may be a solid inner core. The Earth has a solid inner core. But the outer part of the core of Mercury, or at least an outer part, must be fluid to decouple the deeper parts of the planet from the solid shell that participates in what's known as a forced libration at the period of Mercury's revolution around the sun. Now, is it a dynamo? That is the leading idea, because a dynamo would be expected to have a strong relationship between the planetary spin and the magnetic field. You see that on Mercury. If the crust were magnetized, we would expect that when we flew over areas that had been modified, say by a big impact crater, that would take a bite out of the magnetized crust. And we would see magnetic anomalies, variations from the long waves of the field associated with these younger features. We do not.
Well, we're talking about a field which is, let me see, I'm trying to make a back-of-the-envelope calculation. The Earth's magnetic field is half a Gauss.
Yes.
And you're talking about nanoteslas. So that would be 10 to the minus 4 Gauss. I think I did that.
The surface field.
10 to the minus 4 Gauss for Mercury.
Yeah, but we're seeing more than one nanotesla. The surface field of Mercury is 10 to the minus 2. The surface field of the Earth. The dipole moment is 10 to the minus 3.
10 to minus 3.
The dipole moment. So it is a weak field. And
very weak field.
Yes.
It's weak, but it's stronger than Mars.
Yes, Mars has no dipolar field. The only field we see at Mars is paleomagnetic. These are large patches of crust
Right.
that have a coherent magnetization of a sufficient strength that you can measure it with a magnetometer in orbit,
Yeah,
but no global field. So there must be some organizing system which we think is more or less precise.
it must be
It's dynamo
related to
characteristic.
it must be a hydrodynamic.
Exactly.
Yeah,
That's the,
it must be.
yes, we agree with you.
Was Mercury much bigger in the past, and that all we have left is a core with a thin crust?
That is one of the leading ideas for what we're seeing. That Mercury was once about a Mars mass. And if it was hit by a large enough object to remove 75 or 80% of this rocky shell and protect an early formed core at the center, you'd end up with about the right mix of rock and metal to match Mercury. Now, that's not so easy to do. It's easy to hit it. It's easy to disrupt the target. You not only have to remove it from Mercury, you have to prevent it from reaccreting back onto Mercury. So you have to get it away from Mercury's orbital zone around the sun. The way that is thought that might work is if the ejected material is all in very, very fine particles. Now, that's quite a leap, but if you do that, then the kinds of forces that affect small particles and don't affect large ones, like radiation pressure and differential heating, can move the particles fairly quickly outside of Mercury's zone. I want to acknowledge all of this. Yes.
The National Academy recently released a report about the potential damage of solar storms to the satellites around the Earth.
Yes.
So your vestry must be really hardened for that. So
It is hard, but that doesn't mean we don't hold our breath when it's in the path of a very energetic particle stream, a coronal mass ejection. And we've been hit by two so far in orbit. We're also a very interesting outpost on space weather, which is gathered by many satellites, but most of those are about 1 AU. And we have a particular vantage point that's not only at a different, typically at a different solar longitude than the Earth, but is at a different radial position. So we're adding three-dimensional information and some advanced warning to the kind of space weather that you're talking about. Yes?
I was confused by your explanation of how you achieve the delta V of 10 kilometers per second needed to get into the Mercury orbit. I think you said there were two choices. One is to get a very large propulsion system, and
Sure.
I wasn't clear whether you did that.
No.
And the other one is to use the Planet flyby, which takes 7 years, I guess,
Yes.
to get there. Could you clarify that?
Yes. We did not have the propulsive capability on board to impart 10 kilometers per second delta V. When we launched, we had 2.3 kilometers per second delta V total capability. That was making our spacecraft as much propulsion system and propellant as we possibly could, lightweighting everything else. So we were 55% propellant at launch, but our total delta V budget was only 2.3 kilometers. So the standard interplanetary transfer orbit that could be used to send a spacecraft from Earth to Mercury in a few months has this encounter speed of 10 kilometers a second. So we could not go into orbit without making use of multiple flybys of Venus and Mercury. And those trajectories have been worked out in the mid-80s. As you probably know, depending on how you fly the spacecraft by the planet, you can give the spacecraft a boost or slow it down relative to the sun. And the boost method is used for spacecraft that go into the outer solar system. So you want to go to Jupiter, you want to go to Saturn, you want to go to Pluto fast, you fly by an inner planet and you get one of those boosts. But you can also fly by an inner planet and slow down relative to the sun, getting closer. Your spacecraft, your linear and angular velocity closer to that of Mercury. So that's what we did. And that's why it took 6.5 years. We needed all 6 of us. Okay.
Time for 2 more questions.
Robin promised she would say that after 15 years.
Is there an alternative explanation for the loss of crustal mass on Mercury, such as the impact of the solar wind or other solar forces? And number two, could you clarify, sir, the difference between the sidereal day and the solar day?
Yes, let me do the second one first because that's easy. The sidereal day is the day, the spin period as viewed by a distant observer. So when we look from the Earth or from some star and we measure how long it takes Mercury to spin relative to a fixed distant observer, that's about 2 months. Okay? The solar day, it only means something to an observer on Mercury. Or it means something to an imaging system that is trying to look at what part of Mercury is illuminated. And that is the time, a measure of the solar days, if you will, is the time between daily noons. So how long does it take before the sun comes all the way around to be overhead again? And that's 6 months. Now, on Earth, there is a difference between the sidereal day and the solar day, but it's only about 4 minutes.
On Mercury, though, 2 months versus 6 months.
On Mercury, it's 2 months versus 6 months, that's right. And the difference is that the Earth, the spin rate is much faster. And so the difference between the sidereal day and the solar day is very small. On Mercury, because the spin rate is so small, you get this huge difference between sidereal and solar. And in the extreme of 1-to-1 spin-orbit resonance, if Mercury were in a synchronous rotation around the sun, then the concept of the day would no longer have any meaning to an observer on the surface. But there would still be a spin rate matching the year to a distant observer. And so there'd still be a sidereal. And your first question was about, is there another way to remove crust? Nobody thinks that the solar wind bombardment is going to have a big effect on the scale of the thickness of the crust. It's a possible candidate for removing material in the hollows on time scales of millions of years, but we're talking about features tens of meters to a few kilometers across, at most tens or hundreds of meters deep. And so that's, on a planetary scale, that's still small. So in terms of removing crust, the biggest candidate is the very large impact. But the geochemical community is now starting to think about ways that we might be able to match the composition of Mercury without invoking a giant impact, just by having different oxidation states at different positions in the disk of gas and dust from which the planets form. I'm not sure that that's going to work in terms of the total mass fraction of iron that we need for Mercury. We're still making a giant impact. But it's causing everybody to go back to being wrong. I guess we're down to one question.
One more question.
Who wants the last question? Maybe my answer was so long. You can count that last question as two. We're waiting for this one in the back.
What does the plasma spectrometer tell us?
Oh, the plasma spectrometer is looking at ions that encounter the spacecraft. And what for charged particles are thought to be relatively low energy. So it's distinguished from the spectrum, the end of the energy spectrum that's characterized as energetic particles. But the most abundant plasma constituent are protons that are streaming from the sun as part of the solar wind, and many of those protons are apparently captured by Mercury because they fill the magnetosphere that surrounds the planet. But the plasma spectrometer also can go to much higher mass ions, and so is another way of measuring the composition of material in the vicinity of Mercury. And for atoms heavier than helium, those have to be derived from the surface. So sodium is one of the most abundant heavy ions as seen by the plasma spectrometer. And that's also a major constituent of the neutral atmosphere. So there's got to be a source of sodium at the surface, and sodium is strongly involved in the dynamic interaction between the surface and the atmosphere and the charged particle environment. But it's also sensitive to other ions. So it's giving us an inventory of the space around Mercury and helping us to constrain the processes that involve exchange between the surface and that environment.
Thank you very much.
I can't go.
No, you can't quite go yet. In appreciation for your talk tonight, we'd like to present you with this copy of your lecture.